4, and we're looking at comparing two population standard deviations. Fortunately, we do have a function on the calculator to do this. We don't have to use the chi-square distribution. We use something called the F distribution instead. So let's try this example. Researcher Seth B. Young measured the walking speed of travelers in San Francisco International Airport and Cleveland Hopkins International Airport. The standard deviation speed of the 35 travelers who were departing was 53 feet per minute. The standard deviation speed of the 35 travelers who were arriving was 34 feet per minute. Assuming walking speed is normally distributed, does the evidence suggest the standard deviation walking speed is different between the two groups? Use the alpha equals 0.05 level of significance. All right, so we have a lot of numbers here. I'm going to go ahead and label what they're representing. The standard deviation speed of the 35 travelers, so this here would be N1. This is a sample size. And then here we have a sample standard deviation, S1. So this is a sample size and standard deviation of the departing travelers. Next we have the arriving travelers. Here is the sample size, so here's N2, also 35. And then the standard deviation of the walking speed of the arrival group was 34, so I'll call that S2. I'm just labeling these because I want to make sure I put them in the correct position on the calculator. So we're testing two standard deviations, and the last sentence, or the question here, has the word different. Remember that different always indicates that we're going to do a two-tailed test or a not equal to alternative hypothesis. So the null hypothesis is always a statement of equality. So sigma 1 equals sigma 2. So we're using sigma, which represents the population standard deviation. And H1 is that sigma 1 is not equal to sigma 2. So those are our hypotheses. And now we want to find the p-value. So we go to our stat tests menu. So stat, arrow to the right, tests. The two sample F test is way at the bottom, so I'm going to just use the up arrow here. Here it is. On my calculator here, it's the E selection, two samp F test. It's kind of a fancy F here. The F stands for Fisher, who was actually a famous statistician. So let's press enter to go into two sample F test. And we are given the input choice of data or stats. Well, in this problem, I'm given stats. I've been given values of S. So S1 is the first standard deviation. I labeled that. That's 53. N1 is the first sample size. I labeled it right here. It's 35. S2 is the second standard deviation, which is right here, 34. And then N2 is the second sample size, which I have right up here. It's also 35. And then we're doing the not equal to hypothesis. That one's already selected on mine, so make sure it says that on yours. Calculate. Okay, so it gives us the F test statistic. We don't really need that. What we want here is this p-value. So it's about 0.011, so let's write it down. So I'm going to 3 decimal places, so 0.011. Okay, the level of significance was 0.05. So do we reject H naught? And the answer is yes, right? Because P is less than alpha. Anytime the p-value is less than the level of significance, your result is considered unusual or statistically significant. So we state our conclusion. There is sufficient evidence to conclude. There is sufficient evidence to conclude that the standard deviations of walking speed are different between departing and arriving travelers. Okay, let's try one more example. A quality control engineer wants to find out whether or not a new machine that fills bottles with liquid has less variability than the machine currently in use. The engineer calibrates each machine to fill bottles with 16 ounces of liquid. After running the machine for 5 hours, she randomly selects 15 filled bottles from each machine and measures their contents. She obtains the following results. So we have some data in two separate lists here. Is the variability in the new machine less than that of the old machine at the alpha equals 0.05 level of significance? Note, normal probability plots indicate that the data are normally distributed. Okay, so this time we have data values. We were not given the values of statistics, so we have to go into our list. So stat, edit. Okay, I'm going to clear out my old stuff here. And we're going to type in the new data values that we have. So I'll type the values for the old machine into here. 16.01, 16, 16.04, 16.1, 15.92, 16.04, 16.07, 16.05, 16.01, 16.16, 15.96, 15.89, 15.91, 16, 15.92. Okay, and then we'll put the values for the new machine in list 2, 16.02, 15.95, 16, 16.06, 16.08, 15.96, 15.99, 15.97, 16.05, 15.96, 16.05, oops, 5, 16.05, there it is, 16.02, 16.03, 15.94, 15.95. All right, hope I didn't make any mistakes. So this one's not listed for us step by step, so let's go ahead and write our hypotheses. One thing I noticed when I was doing this is that they're kind of in reverse order. It says, is the variability in the new machine less than that of the old machine? The old machine is listed first, so I'm going to use subscripts in my hypotheses because I don't want to get this confused. So the null hypothesis is always that the both standard deviations are equal. I'm going to use subscripts instead of 1 and 2. I'm going to use O for old, and I'm going to use N for new. I'm doing this because I put the old machine data in list 1, so I want to put the old machine standard deviation first. It doesn't matter as long as you keep it consistent. I just noticed that it was asked in a different order than the way the data was presented, so I'm going to make sure I keep track of what I'm saying. Now it says, is the variability in the new machine less than that of the old machine? So I'm going to put the old machine first and write it this way. Now you could write it the other way. You could put standard deviation of new is less than standard deviation of old, but then you need to remember that your new machine data is in list 2. I'm doing this way. I think it's a little bit less confusing because of the way I did it. If I could redo this, I might have put the new machine into list 1, but I didn't, so I'm going to keep it with this kind of keeping the old machine as list 1, the new machine as list 2, and keeping them in that order. So let's try the 2 sample f-tests to get the p-value. Stat tests, I'm going to go up from the bottom. Okay. And the input value is now data because I'm using lists. List 1, list 2. And I'm going to change this to a greater than hypothesis because that's the way I set it up in my problem. Okay, and then we go to calculate. Okay, so we have the p-value right here, about 0.035, I would say, if I had to round it. Okay, so our probability value is 0.035 and alpha is 0.05. So p is less than alpha, which means our results are statistically significant and we will reject H0 in favor of H1. So there is sufficient evidence. There is sufficient evidence to conclude that the variability in the new machine is less than that of the old machine. So I'm kind of restating part of the problem. You don't have to state it in exactly the same way I did. You could have said something like, there is sufficient evidence to conclude that the standard deviation of the, the standard deviation of the contents of the bottle is lower in the new machine than the old machine, if you wanted to use the word standard deviation. The word variability is sort of indicative of standard deviation, but for most of these, there's going to be more than one way you could state your conclusion, and as long as it makes sense, it's fine with me.